Dawn breaks over a misty valley in the Congo. In the half-light, figures descend into hand-dug pits, chipping away at veins of blue-grey rock. They're artisanal cobalt miners, some barely teenagers, hacking out chunks of ore with simple tools, breathing in dust with little if any safety gear. Half a world away, in a gleaming Silicon Valley lab, a prototype AI supercomputer hums to life. Its circuits will soon analyze billions of data points, solving problems at unfathomable speed. These two worlds, distant and seemingly unrelated, are in fact intimately connected. The cobalt clawed from that African soil will become part of the lithium-ion batteries that back up our data centers and power AI robots. The silicon chips in that supercomputer are doped with exotic materials like gallium and tantalum, sourced from hidden corners of the globe. Today, we pull back the curtain on this global treasure hunt for the critical metals powering AI. This is the untold story of AI's hardware backbone, a tale of dirt and data spanning rare earth magnet mines and high-tech chip fabs, Congolese cobalt pits and quantum computing labs. A handful of obscure elements, rare earths like neodymium and dysprosium, cobalt, gallium, niobium, tantalum, tellurium, form the invisible bedrock of our AI-driven future. These raw materials enable everything from GPUs to data center power systems, from the sensors of autonomous vehicles to the quantum processors in cutting-edge research. Yet control of these critical minerals is far from assured. Supply chains snake through single points of failure, often bottlenecked in one country or plagued by geopolitical risk. To a tech investor, these metals may seem esoteric, chemistry-class curiosities, but neglecting them could mean the difference between AI boom and bust. Governments now treat them as strategic assets. New policies, alliances, and billions in funding aim to secure supply. And as East-West tech tensions rise, these metals are becoming pieces on a high-stakes geopolitical chessboard. Tonight, we investigate the critical metals powering AI, the vulnerabilities in their supply, and what's being done about it. Rare earth elements, the magnetic muscle of AI. In 2010, China briefly halted rare earth exports to Japan. Prices exploded overnight. Supply chains felt shockwaves. The world saw how fragile high-tech manufacturing really was. Rare earth elements, neodymium, dysprosium, terbium, and others, form the permanent magnets inside cooling fans, robotic actuators, EV motors, and countless high-speed components in AI hardware. They also power optics, lasers, and precision sensors used in drones, satellites, and autonomous systems. China controls roughly 70% of mining and about 90% of global refining. Western countries are attempting a turnaround. The Mountain Pass mine in California is back online, new separation facilities are under construction in Texas, and Canada and Europe are developing their own supply chains. But China's lead is immense, and it continues to acquire deposits globally. Rare earths are now seen as strategic leverage. Without stable access, advanced GPUs, robotics, and AI infrastructure face severe risk. Gallium, the quiet chip war metal. Some materials don't make headlines, yet underpin the entire tech world. Gallium is one of them. Gallium-based semiconductors power high-speed chips, laser diodes, 5G equipment, and the optical interconnects that allow AI supercomputers to communicate at light speed. Modern AI training depends on thousands of these parts operating flawlessly. China produces about 98% of global gallium. In 2023 and 2024, Beijing imposed export restrictions, triggering price spikes and fears of a supply crunch. It became clear that a single administrative decision could slow or halt high-end chip production in the West. Europe is now building new gallium production capacity. The US is exploring gallium recovery from zinc and alumina processing. But these solutions will take years to scale. For now, gallium remains a choke point. Cobalt, AI's energy backbone. Data centers cannot lose power, even for a second. That reliability depends on lithium-ion batteries, and those batteries depend heavily on cobalt. About 80% of cobalt is mined in the Democratic Republic of Congo. China controls most refining capacity. This creates a dual vulnerability: geographic concentration and geopolitical dependence. Cobalt is critical for high-energy density batteries used in robotics, servers, drones, AI hardware, and backup power systems. Ethical concerns persist. Artisanal mines, child labour, unsafe conditions, yet global demand continues to grow. The US, Canada, Australia, Finland and Indonesia are advancing new cobalt projects. North America is building refining capacity for the first time in decades, but for now the cobalt supply chain still runs through the Congo-China axis. Niobium, the metal behind quantum AI. Niobium is a strengthening agent in high-performance alloys used in aerospace, EVs and industrial infrastructure. But its most important role lies in quantum computing. Niobium circuits form the superconducting pathways inside quantum processors. These chips operate near absolute zero, with almost no electrical resistance, enabling computation speeds that could redefine AI capabilities. Over 85% of the world's niobium comes from a single mine in Brazil. Most of the rest comes from Canada. Such concentration makes niobium one of the most strategically sensitive minerals on Earth. Western governments now classify it as essential for national security. New projects in Canada and the US are in development, but global dependency on Brazil remains. Tantalum, the power stability. Metal. Tantalum is the hidden hero of modern electronics. Its capacitors store and release energy with exceptional efficiency, stabilizing power delivery in GPUs and servers under heavy loads. Without tantalum capacitors, AI processors would experience voltage instability and system failures. Historically, a large portion of global tantalum came from conflict regions in Central Africa. Today, supply has diversified. Australia is now a major producer, along with Brazil and Rwanda. Recycling provides a growing secondary stream. Still, the market is small and volatile. Shortages have disrupted major tech launches in the past. As demand for AI hardware surges, tantalum's importance grows. Tellurium and the supporting cast. Tellurium powers advanced memory technologies and thin-film solar panels used to run energy-intensive data centers. Germanium underpins fiber optics and infrared sensors. Indium enables displays and high-performance chip interconnects. Even copper, used in massive quantities, is projected to face multi-year structural deficits. China dominates many of these markets, often producing 60 to 75% of global supply. Export controls on germanium and gallium in 2023-2024 revealed how quickly access can shift from stable to precarious. The US, EU, Japan, Canada and Australia are launching coordinated responses. The Inflation Reduction Act, the Critical Raw Materials Act, and the Minerals Security Partnership all seek to build secure, allied supply chains for the minerals AI depends on. In conclusion, AI doesn't run on code alone. It runs on cobalt from the Congo, gallium from Asia, niobium from Brazil, rare earths from Inner Mongolia, tantalum from Australia and Rwanda, tellurium from copper mines, and dozens of other minerals pulled from every corner of the planet. Every breakthrough in machine intelligence begins with physical materials, mined, refined, alloyed, and transformed. The nations and companies that secure these resources will shape the future of AI. Those that overlook them may find themselves vulnerable to shortages, export controls, or geopolitical leverage. The future of AI is written in data, but its foundation is carved in metal.